Hey guys, welcome back. We got Le Chatelier's principle and reaction quotient in this video. So hope you're doing well. And we'll just dive right into reaction quotient. So reaction quotient. And that'll be called Q. Reaction quotient Q. This describes the composition of a system. So we're describing the composition of a system. It's not necessarily at equilibrium. That's very important. It helps determine if we're at equilibrium. So if you remember, we have reactants. I could spell today. Let's try spelling correctly. Reactants. Going back and forth to with products. So you remember K is the concentration of products over reactants. And it's temperature dependent. So K is a measured value at, let's say, 25 degrees Celsius or 1000 Kelvin or 200 Kelvin, whatever the temperature happens to be. Well, Q is also the concentration of products and over the concentration of reactants, just like the equilibrium constant expression is. But Q tells us the conditions of the reaction at that time. So Q does not have to equal K. Q tells us where we're at reactant concentration, product concentration, and relative to the equilibrium position of reactant concentration to product concentration. So we might add something to an equal system. We might take something away from a system. How is that system going to respond? So, of course, there are three possibilities. The first possibility, so K, K, and Q, Q, and Q. Q could equal K. If Q equals K, we're at equilibrium. That makes sense, right? So I look at what my concentration of whatever component, whatever species in solution. I find that concentration of that species. It happens to be the equilibrium concentration of the species under these conditions. We're at equilibrium. That's wonderful. Now, Q can be larger than K. If Q is bigger than K, right? Q is bigger than K, that is too many products and or not enough reactant. With too many products, not enough reactants. So that means the reaction, we're going to say shifts to the, well, let's look at it before we think about this. So if there's too many products, if products is too big, it means this is too big compared to reactants. So that means we have to put some products go back to reactants. So this direction is going to go more. So that means it would shift to the left to the reactants. Conversely, if Q is less than K, so K is bigger than Q, that means it's the exact opposite. Not enough products or too many reactants. So this reaction shifts to the right to the products. So we're just comparing Q to K at any situation, and we'll see where we're at in terms of equilibrium. Are we still before equilibrium. Maybe we have too many products, like we're past equilibrium, we gotta go back. And so that is the reaction quotient Q. And it just tells you where you're at in terms of K, where we're at. Now, the next concept that's really closely related to this is Le Chatelier's principle. Le Chatelier's principle, when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. The goal is to restore equilibrium. So that's Le Chatelier's principle. When a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. There are 3 ways to disturb a system that we're going to talk about. So in terms of possible ways or methods to disturb a system. And those would be concentration. When it comes to concentration, we can either add product, we could add reactant, or we could remove product or remove reactant. So if I add product, what happens? Well, it's just like Q. So you can think of Le Chatelier's principle as a teeter-totter, so to speak, if you've ever done this. And this teeter-totter has a position. It does not have to be horizontal, like a balance. It could be here. It could be there. It could be there. It doesn't matter where they are. However, if we add too much to one side, that side's going down, we actually have to take some of this purple and go on the other side to balance it back. And that's what we're talking about. So if I add product, that means the reaction will shift left to reactants. If we add reactant, the opposite happens. The reaction shifts right to products. If we remove product, it's the same thing. So I'm going to remove product. The reaction has to actually fill back in the product I removed. So the reaction will shift right to products. And conversely, if I remove reactants, the reaction will shift back left to reactants. So that's concentration. It's very similar to Q. Le Chatelier's principle is basically the same thing. Q just has numbers, whereas Le Chatelier's principle, we're just looking where we're adding and where the basically teeter-totter is going to go, where the reaction is going to proceed to equal out, to get back to Q, back to K. The next way we can talk about is temperature. We talk about disturbing a system, and that is temperature. There's 2 types of reactions. You have exothermic, where heat's produced, and you have endothermic. Heat's absorbed. So for exothermic, we just treat heat as a product. Endothermic reactions, we treat heat as a reactant. So it's just a product or it's a reactant. So heat, when we talk about an exothermic reaction, I have CH4, oxygen gas, making carbon dioxide, water, and heat. And we treat heat as a product. Endothermic reaction, I have heat plus NO2 going to N2O4. Heat's a reactant. So we just treat it that way. The last way we're going to talk about disturbing a system is through pressure. So there's two ways, pressure and it's technically volume. So if we increase pressure, and or decrease volume, the reaction goes to fewer particles. If we decrease pressure and or increase volume, the reaction goes to more particles. And an example is probably the best way to explain that. And that'll be the second example we'll do. So the first example is consider the equilibrium for the water gas shift reaction, carbon monoxide, water going to carbon dioxide, and hydrogen gas. Use the Chatelier's principle to predict how the concentration of H2, so we now know how this concentration of H2 up there will change when we disturb the system. So if I add CO, so the first one, I'm going to add CO. If I add CO, that means concentration CO is too big, so some of this will have to go that way to make CO2 and H2O, which means I'm going to actually increase the concentration of H2. Now, adding CO2. CO2, add here. That means this side is now too big, so we're going to actually have to take some of the H2 and come over to make some water. So that is going to decrease the concentration of H2. Removing H2O. So if I remove H2O, so taking this out, these guys will have to come in to fill in, and so I'm also going to decrease concentration of H2. Removing CO2. So now we're removing CO2. The opposite is going to happen. CO and H2O have to be made. So these guys have to fill in over here because this is leaving. That works out. So H2O increases. H2 concentration increases. And that's all it is with Le Chatelier's principle. Number two, does the number of moles of products increase, decrease, or remain the same when each of the following equilibria is subjected to an increase of pressure by decreasing the volume? Just as like a balloon, a syringe, all you're doing is you're decreasing the volume so the pressure goes up. You squeeze a balloon, you decrease the volume of the balloon, the pressure goes up. And if you do it too much, it pops. And if you have kids in the room, it's never fun. So let's look at B first. And the reason I'm going to look at B first, I have a 2 moles of CO gas, a solid, and I have 1 mole of CO2 gas. Now, if you remember the ideal gas law, 1 mole, any gas that's ideal, occupies 22.4 liters at STP, which is 273 Kelvin and 1 atmospheric pressure. Well, doesn't matter the conditions. The point of this statement is that all gas molecules are relatively the same size, so they take the same amount of space. So if we are going to increase the pressure by decreasing the volume, we want to go to a side that takes up less space. So 2CO gas has 2 moles of gas. For 1 mole reaction. C is a solid. It has 1 mole of gas. So technically speaking, the product side here is half the size as the reactant side because we only have 1 mole of gas versus 2 moles of gas. And solids are very, very small compared to gases. When we talk about density of solids 1,000 times more. That means that the reaction will go to the right. Why? Because smaller. The right-hand side is smaller. So if we're increasing pressure by decreasing the volume, right, the reaction goes to right to products because it takes up our space. So now if we go back to the A, coefficients 1, 1, 1, 1. There's actually no change here. And the reason there's no change, it's the same amount of moles gas on both sides. C, what's happening with C? Well, for C, I have 1 mole and I have 2 moles. So which side is smaller? N2O4, so the reactions are going to go left to reactants. That's what we do with gases. It's whatever takes up the least or most amount of space, depending on what we have. 3. A platinum catalyst is used in automobile catalytic converters to hasten the oxidation of carbon monoxide, which is why they're so expensive. And there's reaction, you got carbon monoxide, oxygen on the platinum catalyst going to carbon dioxide. And delta H is negative. That technically means plus heat here, right? Because heat's coming out. Heat's a product of this. For A platinum catalyst is added. Well, what does a catalyst do? Catalyst speeds up a reaction by lowering the activation energy. Right? All the platinum catalyst does is lowers EA. That means there's no change. So it speeds up the reaction in the forward direction and the reverse direction, but it does not actually change the concentrations at equilibrium, which is probably a good thing. The temperatures increase. So if I add heat, where am I adding? I add heat to this side, that means the reaction will shift to the left. We're going to shift left to reactants. So when we talked about the amount of CO, it would actually increase. The pressure is increased by decreasing the volume. Well, we have how many moles of gas? 3 moles of gas on the left and 2 moles of gas on the right. So that would assume that I would go to the right, which means concentration of CO would decrease. The pressure is increased by adding argon gas. Well, argon is AR, and that is inert. It's inert gas, which means there's no effect. Argon's not involved. Kind of like if I can't go to Dunkin' Donuts and eat donuts, but let's say I could. If I go to Dunkin' Donuts and eat 2 donuts a day every day I come to my office and sit here for most of the day, what's probably going to happen to my belt? It's probably going to get tight. That has nothing to do with your weight. I can eat all the donuts that I want. I can gain 10, 20, 30, 40 pounds. You didn't gain any weight. Conversely, I could lose 10, 20, 30, 40 pounds, and it doesn't affect you at all either. So when we add argon gas to a mixture, nothing's going to happen. The total pressure is going to increase, but nothing with the reaction. For E, we're going to increase the pressure by adding O2. Well, O2 is in the reaction. O2 is right here. So if I increase O2, we're going to have to shift to the right. And if I shift to the right, carbon monoxide will decrease. Number 4. Suppose you have UO2 plus 4HF, which don't do this at home. Do not buy uranium. Going to UF4 and water. And it's reached equilibrium. Predict the effect that each of the following changes will have on the equilibrium position. Tell whether the equilibrium will be shifted right, left, or not affected. So A, if I add UO2, we're going to add UO2, uranium for oxide. What's going to happen? Well, adding a reactant, won't it shift to products? Ooh, I don't know. It's a solid. Since UO2 is a solid, there is no effect. As long as the solid's there, the equilibrium is reached. There's no effect, no change if I add more solid. I just add more solid. Now, if the solid disappears, then there will be an effect. But if you have 1 gram or 10 grams or 100 grams, it doesn't really matter. B, the reaction is performed in a glass reaction vessel. HF attacks the glass because HF does dissolve glass and reacts with the glass. So that means if HF is reacting with the glass, we are removing HF because it's being a reactant for another reaction. So you're removing HF from the system. If we remove HF, that means the reaction is going to have to go back to fill it in. So the reaction will shift left. If C happens, water vapor is removed. Removing this, that means the reaction will have to shift right. Number 5 is a reaction quotient problem. So number 5, we got the equilibrium constant of 0.09. What is the K expression? Well, K is equal to the concentration of HOCl, hypochlorous acid, squared, all over concentration of H2O. Yes, we have H2O in there. Why? Because it's a gas. And dichlorine monoxide. That's our equilibrium constant expression. It's also the reaction quotient expression. So for which of the following sets of conditions is the system at equilibrium? And for those which are not at equilibrium, which direction will the system shift? A, we have 1 liter flask with 1 mole, 0.1 mole, and 0.1 mole. So Q is equal to HOCl. So we're going to do it this way, where we have 1.0 moles in 1.0 liters squared all over 0.10 moles of H2O over 1 liter and 0.10 moles over 1.0 liters. And we can figure out Q that way. And we get that for Q would be 100. And how does 100 pair to 0.09? 0.0900. It sure looks like Q is much bigger than K. Q is much bigger than K, so that means the reaction shifts left to reactants. Whoa, sorry. B, a 2-liter flask contains 0.084 moles of HOCl, 0.08 moles of Cl2O, and 0.98 moles of water. So for B, we'll use this color. So I got Q equals HOCl is 0.084 moles of HCl in 2.0 liters, and that's squared divided by 0.98 moles of water in 2.0 liters and 0.080 moles in 2 liters. And you guys can get tricky with the twos, and if you want to do some math, but I would just use your calculator and solve this. I'm going to solve it, and I get 0.09, which means I'm at equilibrium. So hopefully you're thinking this is not as difficult as it maybe looked. For C, Q equals my 3 species in their concentrations. So HOCl is 0.25 moles. Water is 0.56 moles. And Cl2O is 0.0010 moles. The volume is 3.0 liters for everybody. And for Q, we get what? I get 111, which compared to 0.090, Q is much bigger than K. So the reaction will shift left again. Now in class, a lot of times students want to assume that C would be a reaction to the right, because we did left, equilibrium, they think right. Don't do that. Always do the reaction. Don't assume. We don't want you to assume. That's not what we want in science. We want to do the test. What do I get? Do the test. What do I get? We want to go in objectively without bias. So even these questions, like I would love to do this where everything's A except the last one's B. Just silly stuff like that that are blatantly obvious questions, but we let I can't be that. What does the data say? What does the data suggest? It's a very, very important thing. One last one. 6. Which of the directions will the equilibrium be shifted for each of the following changes? So 2HI going to H2 and I2. H2 is added, so if we add H2, reaction's left. If I2 is removed, reaction's right. If HI is removed, reaction's going to the left. Argon's added, no change. The volume of the container is doubled, 2 moles on each side, no change. Temperature is decreased, exothermic reaction. Plus heat. I remove heat, going to the right. I got number 50. You know I had number 50. Well, let's do number 50, and then we'll be done. Nitrogen dioxide dimerizes according to the reaction. It gives you Kp. It gives you a container with each concentration of NO2 and N2O4, 298 Kelvin. Is the reaction equilibrium? There's your question right there. Is this reaction at equilibrium? If not, in what direction will the reaction proceed? So it's either at equilibrium, it'll be no to the right or no to the left. So So let's see what we got. The expression for K would be concentration of N2O4 all over NO2 squared. Now I want to point something out that I noticed. I have Kp here, and we're having moles, and liters. So the question is, do you want to convert your moles of each of those reactants to atmospheres of each of those reactants, which you can do using the ideal gas law? Or do you want to change Kp to Kc? Well, since I'm assuming you already know how to do the ideal gas law, we'll do Kp into Kc. Kp is equal to Kc times RT delta N. Kp is 6.7. Kc, I don't know. 0.08206 liters atmospheres moles Kelvin times 298 Kelvin times delta N. 1 minus 2. 1 minus 2. Kc then is equal to, I got 164. So now I can plug in this reaction of Q. Q would equal moles. I have N2O's on the bottom of 0.055 moles and 0.082 moles of N2O4, 2.25 liter container. For Q, we get 61. So Q is less than K, which means the bottom number is too big, the top number is too small. So the reactants are too big, products are too small, so we're going to shift right to products. That is Chatelier's principle and reaction quotient. Examples. Hope that helped out, and we'll see you next time.